Hello, and welcome to my video in which I apply the Lagrangian and the properties of the Lagrangian to the double pendulum and its equation of motion. And I'm going to be doing this in terms of the two generalized coordinates theta and phi. And I went ahead and made the masses the same and the length of the two rods the same, as well as making the rods massless themselves. And my hope in doing this was that the algebra would be a lot simpler and a little bit less convoluted, which it was, although still very difficult. Or tedious, not necessarily difficult. But let's go ahead and calculate our kinetic energy, as that's one of the important parts of the Lagrangian. So we just formulate our position vectors in terms of our two coordinates, take time derivatives here and here, and square both of those. So that's this expression and this one. And once we plug it back in through some simplification, we end up with our kinetic energy equals this expression. And that's the expression for the way I have chosen to formulate the double pendulum problem. We also need our potential, which is rather straightforward looking from the diagram. Just looks something like this, which simplifies to this. And now that we have both of these pieces, we can go ahead and formulate our entire Lagrangian. So here's our Ke minus the U. So now we need to start taking the partials with respect to each of those coordinates. And we know by the properties of the Lagrangian that this term should be the same as this term. So we will go on to set this expression equal to this one. And likewise with phi, this expression equal to this one. And it's a little bit messy. The algebra is very messy. I had to turn the sheet horizontal to fit it all. But these are the two expressions once we set those things equal to each other. Through some simplification, all of our masses here fall out of this equation completely. We never see them again, which is really cool. And this expression simplifies even further to become this one. So equation 1 turns into equation 3 right here. There's some canceling out going on. And likewise, with this equation, all the masses fall out just as the previous one. And through further simplification, equation 2 becomes equation 4. And this took a very long time. And this is still not really complete yet. But I just want to pause here to notice something kind of interesting, sort of profoundly simple. But if we consider phi double dot, and we assume that theta dot equals 0 for all time, essentially that just means theta is just fixed in its place for all time. Then that means theta dot dot is also 0 for all time. In our ODE, equation 3 simplifies, if we make that assumption, to the equation of a simple pendulum. Phi dot dot equals minus g over L sine of phi. And the exact same thing happens with our theta double dot equation. We end up getting theta double dot equals minus g over L sine of theta. And if we go back up to our diagram, we can actually see intuitively why this should be the case. Let's consider theta double dot. If we assume that phi dot equals 0 for all time, meaning that phi is simply fixed throughout all time, what ends up happening is these two masses connected to each other end up combining into one big mass. And that causes only this arm to rotate and creates just one simple pendulum. And likewise, if we considered the equation of motion for phi, and theta dot equals 0 for all time, then really this rod stays fixed, stays right here. And the only thing that moves is really this rod and this mass. So we can essentially treat the whole system as just this one simple pendulum. And it should have an equation of motion for a simple pendulum too. So I thought that was something profoundly interesting, which I didn't really expect to do when I was doing this algebra, but it makes a whole lot of sense after I saw it. But we can't stop here, because we have two double derivatives here, and for the sake of the computer simulation that I drew up based on these equations, we need only one second derivative in each equation. So I substituted these into each other. I ended up with this equation and this equation. And it was very tedious. I ended up missing this minus sign here, so that when I first ran my code, the pendulum was behaving really strange, and there were sort of fictitious forces in our system. But once I found that this should be a minus, the motion of the double pendulum simulated really does look very similar to a real double pendulum. So these are equations of motion, which I use as a basis for my program here. And I've done this in VPython simply because I have experience with it and I think it's really intuitive. And it's very good at modeling sort of physical stuff. But here are sort of all our parameters, t, our time step dt, our generalized position, generalized velocity, generalized acceleration. And then these numbers are just sort of the initial conditions on the right-hand side. These are our two position vectors. There they are, as we wrote them in our sheet here, R1, R2. And then these are all the visuals. So these are the arrows for the rods and spheres for the masses. And originally with these, I had a graph that was graphing kinetic, potential, and the total energy. But it slowed my program down a lot, so I've commented it out as well as this part. But I'd like to keep it there for future use. So, and then here's our while loop, and all this while loop really does is it just updates everything every single time step. So here we calculate our values for our new accelerations based on the equations we found right here and here. And we use those accelerations to update our velocities. And then we use both the velocities and the accelerations to update our positions. And these are all generalized positions, generalized velocities, generalized accelerations. I just don't want to say generalized so much. And then here we update our position vectors of the masses. And then these 5 lines just update all the visuals. So the rods and the masses, just their positions. And if you notice, I've also added this part for our second mass. And what this will do is for every point in space that our mass goes through, it will leave a red trail, which will really show us just how chaotic the double pendulum is. And last but not least, we update our time so that the while loop doesn't go on forever, which is great. And this line sort of creates the rate of animation speed. So we will run our program here with these initial conditions and see what it looks like. Yeah, so as you can see, the behavior is really similar to a double pendulum. I can't think of any sort of behavior this has that it shouldn't have if it's a double pendulum. The only drawback to this kind of program is that we're doing discrete time step approximations, which means, and I've seen this when I added the graphs into the program, but that even though theoretically energy shouldn't be leaving this system unless we program in friction and drag, which I have not done, even though theoretically energy should all be conserved, because our approximations are just that, approximations, energy sort of mysteriously disappears out of the system. And you can kind of actually tell with this example. I mean, the pendulum goes up so high in the beginning, and then it just sort of sticks around near the bottom, near the end. It doesn't seem to have a whole lot of energy left by the end, and that's just due to the nature that we're approximating the motion. We're not using a deterministic formula for the motion. And so you can see it's just sort of going back and forth down here, a lot less energy. But if we made our time step smaller and smaller and smaller, this error in terms of energy should also go a lot smaller. It should be proportional in some way to our time step. And we can even go on to change some of these parameters. Maybe we make the rods shorter. Maybe we give a little bit less velocity here. Maybe we make the initial acceleration here different. Maybe we change the initial angle. Let's say maybe we change this to pi/3. We can run that and everything will adjust accordingly. And we still have double pendulum. Obviously the motion is very, very different from previous, but we should expect that. So I hope you learned something about both theoretical physics and as well as computer simulation and modeling. And so yeah.